My name is Leonid Schifrin, and I work in the ECE group at Wolfram. And today, the topic of this talk is using the dataset query language to query relational databases. So the title is rather ambitious, and I guess the reality is not as bright as the title may suggest. But so this will be mostly the sort of very experimental. Uh, this will be a discussion of very experimental direction, where I will only be able to show just a few simple results. Uh, but uh, but I think that the direction is potentially very fruitful, and since many people love dataset and it's one of the, or maybe the most used kind of front end to data manipulation in Wolfram language, then being able to use it for some data manipulations outside the in-memory data uh, is should be appealing to many people. Um, so the summary and goals of these are on this slide. So what we try to achieve in this experiment is to connect dataset to various two-dimensional data formats. And in the first place, relational data, because of both of its importance and because it's a non-trivial use case for this experiment to try. And then what we'd like to do is to import existing relational data as nested dataset and run dataset queries against various data backends, in the first place, relational backends. And this project builds on dataset and databases. Database is a newer version of relational database connectivity introduced during this conference by Carla, but first appeared in version 12. And so the main problems to overcome when we go along this path are listed here. So the biggest one is probably the impedance mismatch between hierarchical and tabular data models. But then there are others, like there are certain restrictions of what SQL or relational data or flat data backends can do, and dataset is very rich, has a very rich query language because it essentially allows you to use the entire Wolfram language to do the queries. So not all dataset capabilities we will be able to support, and that's clear from the start. Now, the workflows that we can consider and envision here, I've split in two types of workflows. One is that we have the Wolfram language side data set, and we can back it by certain flat or relational data, and then perhaps use dataset query language to query that data. So in that sense, we could use some other backend as a storage mechanism for data which originated from Wolfram language side. And the other workflow is when you have some data externally existing in some relational backend somewhere, and you want to use dataset query language to actually be able to query that data. Uh, so I want to start with the quick refresher on some somewhat deeper things about dataset. And since I don't have much time, I will skip the very basic discussion of what dataset is. So I'm assuming that people probably know what a dataset is or have run some few basic queries against a dataset. But what not everyone may know is that the dataset has a internal type system, which is rather simple, but which is very useful and which underlies much of dataset's power. So there is a simple example dataset here, which is, I'm sorry if this is a little bit small. I might try to change the magnification for this. Actually, I'm not sure if I can easily do it from here. But in any case, this is a simple this is a simple data set on planets and mountains. And if we look at its type, then it's a certain expression which contains, some things such as atom, vector, struct, a sock, things like that. So it's completely inert, and it represents the type of this data set. So basically it says that the key is anything atomic, either Earth or Mars, but in general it could be just a string. And the value is itself a vector. So this is a list of structs. Structs are essentially associations of certain types of any length. And then there are a number of atomic types that dataset supports. These are some of these types are very well known. Some of them are more special, but these types dataset considers atomic. And there are also composite types, which are essentially vector, sock, struct, and tuple. And there is this table here, which basically shows that uh, you can consider these types along two dimensions, which are either the type represents a homogeneous or inhomogeneous container, or whether the type represents a list or an association. So vector is a homogeneous list of items, then tuple is the inhomogeneous list of items, and then a sock is a homogeneous association, and struct is like inhomogeneous. So struct is like a data type, like uh, typical struct that we know from other languages. Um, so it is. There are also some special types like any type and unknown type, but a more complex example would be from the example data on the planets data set. And its type looks more complex like this. But what's important is that this type is a metadata that exists separately from the data in a sense. They're all unified within this dataset wrapper, but it's very important that dataset knows about these types. And what the reason I'm discussing this is that what I'm going to show is an extension of this idea. So the main question to answer is, how do we map the dataset query model to the query model based on flat or relational data, which essentially is non-hierarchical. It's based on flat data tables. Um, so it turns out that this notion of type is absolutely essential here. So to illustrate that, I'll quickly go through the in-memory dataset example first. So if we take that same dataset with planets and mountains that I was showing before, then the first thing I'm defining is what I call a schema. And the schema is a extending version of dataset type. In addition to a dataset type, which it shows in a somewhat different way. So you can see the same as sock, vector, struct, all these kind of same types. But it also has, you see, there are these fields which have these weird names. And so what happens is that when we try to flatten this data set or to map the hierarchical data to the flat data, we come up with a certain field names for the underlying flat data container, the place where the actual data will be stored. So this notion of schema allows one actually to flatten this data set in such a way that it will still contain all the necessary information about the origins, like from where in the hierarchy a given field was coming. And so that would allow this mapping between the hierarchical data set and the flat data set. And in particular, that would allow us to compile the queries. So there are these field mappings that I will just, I don't know why it's not showing that, but it basically shows which fields on the new flattened data set, how they are related to the hierarchical fields in the original data set. And there is also inverse mapping you can do, which shows the inverse thing. So what happens next is that we can define something which I call an abstract flattener, which is an expression that basically instructs you what you have to do to convert the hierarchical model into flat. And then this abstract flattener, it can actually be compiled depending on which backend you're targeting. And in this case, we are targeting just the memory backend, and I'm generating this kind of function. And if I apply this function to the original data set, what I'm getting is a flattened data set where I have now all the data is completely flat. And then now I can define the abstract unflattener, which basically tells you how to reconstruct the original data from the hierarchical data from the flat data. And then um, I can compile this unflattener, and this example shows how I can generate the compiled unflattener for in-memory data. And if I simply apply this to the flattened data, then I get back the hierarchical data. So the in-memory example I used because I wanted to introduce these notions of flatteners and dataset schema, which will be very useful also for the relational part. Now, I know that I was going very, very fast through this, but what I wanted to mostly bring across is this main idea of mapping between the hierarchical data and the flat data, and the central notion of this sort of a schema, which is essentially an extended version of dataset type, which is extended by the rules of how you translate hierarchical fields into some uniquely named tabular fields. Okay, now let's go to the actual example with the relational data. Here we'll connect to the relational database. This part is completely standard. It's just the same database that has been used in the tutorial, for instance, in the documentation and in Carlos' talk as well. I've done that already, so I'll skip this part. Now, so here is this database. I don't know if this is good enough. Let's try to make it bigger. So basically, this is there are a number of tables here. There are some offices, then there are employees who work for this office. They service some customers. Those customers, they make they place orders and they make payments. And so the other tables are more about the types of products that are being sold in this hypothetical store, but we will not be interested in the entire database here. So what we'll do, we will create the relational data set from the subset of this database. And so this is the spec that we are going to use to create it. So this basically is a part which is containing employees. Then each employee has the number, last and first name, and then they have customers, and the customers themselves, they have a number of fields. In particular, they have payments and orders, which themselves are separate tables, so separate collections of things. So if I execute this, what I'm getting is what I call here relational data set. It's an opaque object. But what's important about this object is that, okay, it has this spec and has the same notion of dataset schema as I was introducing before. And it also has the relational database from which we actually construct this. Now, let's try to get some data out of it. So if I call normal on this object and then wrap it in dataset, I should get some data, and that's going to be a raw flattened data. Now, in fact, here already, we had some SQL query running. So if I wrap it in this wrapper that shows the generate SQL, it should hopefully show you a pretty large generated SQL that was generated to actually import this flattened data. And if I call dataset on this guy, it will both do the same thing, importing flat data, and it will unflatten it using the same sort of technique of using those compiled or abstract or compiled unflatteners. And this is already the sort of the flattened data. You can see that there are customers, there are basically employees, customers, and the customers have some orders, some payments, and so on. So we can actually look at this schema. So if I do DS.
Leonid, let me jump in. Carlo has a question.
Sure.
Your screen is done. I was wondering under payments and orders why it shows as an association if it's limitation of because those are structs, right?
Yeah, I was also wondering that, and I came to a conclusion that it's a limitation of the data set formatting for too deep. When well, maybe not a limitation, maybe it's intentional.
Okay, and the other thing I wanted to ask is like if you scroll up when you give that you give the structure for the relational, that specification there. Do you think it would be possible to have something that says start from employees and like follow everything 2 levels down?
Yeah, I'm sure.
And just build, the spanning tree from that point.
Yeah, I'm sure it would be possible. Here, I just was specifically willing to keep only specific fields and things, but yeah, I'm sure we can automate that.
Okay, thanks.
Mm-hmm. So basically, this I just wanted to show. Let me see. Okay, I just wanted to show the schema in slightly more detail, just to explain that it's the same object we are familiar with from the, well, I don't know why it shows it in this way here with all this weird sizes of fonts, but basically this schema is has exactly the same structure as the schema I was showing before for the flat data in memory. The difference is that now we have relational data because essentially what happens is that each some of these levels, like this level struct here, you can think of it as having a data source being a particular table in a data set. And then this here shows, well, it's a sort of a symbolic representation of a query in a database, which you would need to run to actually construct this data, or get the data out of this database table. So the difference with respect to the flat thing is that now we don't have a single data source in a sense. We have multiple data sources if we view every database table as a separate data source. So for example, here, the SOC level represents the collection of things, collection of, in this case, employees. And the struct level represents the set of data for a specific employee. So these 2 levels represent rows, a SOC, and columns, struct, of a database table, which is this employees table. If we open this struct further, and if we look at the customers, we will see that customers also has this a SOC and struct level. So this is rows for the customers, this is columns for the customers. And these are the inner things. So this is a sort of a separate data source in a sense. I mean, conceptually, obviously, this is the same relational database with multiple tables. So this is important to understand the mapping between the levels of the data set and the tables in the relational database. But now let's try to run some queries before we run out of time. So this here is a simple query. We simply pick a specific employee number and then a specific customer. And so what we get back is another relational data set. So what happens actually is that this compilation, no data has been manipulated so far. What compilation does, it changes the underlying dataset schema. You can now it starts on a struct, and so we completely eliminated these first two levels of dataset, as would have been the case also for the in-memory dataset. And so we only start with this struct, and there are some changes on this struct that I'll show later if I have the time. But anyway, if we now only at the point when we call dataset on it, it will actually do the actual query against the database. So it will generate a SQL. I should probably just show. So if we wrap it in this wrapper, it will hopefully show us the well, let me see, did I actually run this? Because it doesn't show. That's a bit strange. I was hoping that it would actually show us the generated SQL, but yeah, let me see if I can understand why it doesn't. Yeah, well, maybe I should have changed the order of operations here. Yeah. So, and you can see there are these where conditions here, which basically filter for the customer number, and there is another one here, which filters the employee number. And here is the result, which has been unflattened into the data set in memory. Once the flat data were important into the kernel. This here is a more complex query. And this one selects all employees whose name is short, so to speak. So this full name, which is first name underscore last name, is smaller than 10. And then the picks the customers and selects all customers from France. And again, when we compile this, we get back the different relational data set with the modified schema. And when we run it, okay, let me just wrap this with SQL again. If we run this guy, I hope it will show us. So as this, you see this is where it filters the full name, and this is where it filters that they have to come from France, and this is the SQL has been generated, and this is the result. So I think the point to that these examples had to illustrate were that this mapping would allow us to potentially compile truly nested dataset queries into SQL and get back the result, which we could still present hierarchically. But the actual query will run against the SQL. I'm running out of time, so I will probably not show much of the internals, which I was going to show, but some of them follow along the same lines as for the in-memory data set. And so I think main things I kind of explained already. So speaking about the progress was this. Well, one thing to understand, which we are in the process of, is to understand how all these primitives used in the data set play together and how they can be translated into the relational queries. But we have this intermediate representation, which is a schema, which is suitable for code generation for these queries. And so for targeting SQL, we will need basically to figure out the mapping between dataset and SQL query models, which I already mentioned. There is an impedance mismatch, and which we have to overcome. Like, for example, group by and other things behave very differently, and group by is hierarchical, while relational group by is not. So we have to do something about it. But there are some strategies to generate SQL which will probably which we can envision so far. But so this is a very beginning, but this hopefully was giving a taste of how it could be potentially when we develop this. Well, that's all. Thank you. And if there are any questions, I probably don't have much time for answering, but maybe one very quick or two. Thank you very much.
Thanks, Leonid. Questions? So Leonid, this flattening, unflattening, it sounds like you invented some sort of general mechanism for converting between like SQL and NoSQL databases. Is that?
Yeah, I guess you can probably say that. I think, yeah, because the thing is, since we have this abstract layer of flattening and unflattening, that abstract layer can be then compiled to a specific representation.
Right. It seems like you could almost use a NoSQL database that had a back end of an SQL database with this type.
Yeah, well, Todd, I'm not sure, but I hope it is as general as you suggest, but we'll see.
I think I think it actually goes the other way around. Like, if you take a general NoSQL database and you want to serialize this to SQL, then the data might be too dirty to do that. In this case, what Leonid was showing is you take something that's already well represented in SQL and you represent it as something that is NoSQL. But going the other way around might prove to be a lot more difficult because, I mean, if the data is very dirty, it's difficult to construct a reasonable schema out of it, I think.
Yeah, that's a good point. Yeah, that's a good point. But I think the NoSQL is a whole separate story. Although I would think this approach potentially could be used there as well. But as Garl said, it's more about doing dataset queries against various backends, be that NoSQL or SQL. But if we want to map from one to another, that's going to be harder.
All right. Thanks, Leonid.
Thanks, everyone. Thanks, Todd.